Hello everyone and welcome to lecture 42. And in our previous lecture, we have seen how to draw the long run cost curve by using three different short run possible scenarios, right? And just a quick recap, we were given three possible short run cases where each short run had a certain amount of capital, k prime equal to 5, k double prime equal to 8 and k triple prime equal to 12. In each of these cases, I had a short run cost curve, and the key takeaway there was that as you give labor more amount of capital to work with, labor is going to be more productive. So, the k double prime short run cost curve is going to be a lot flatter than the k prime short run cost curve. The k triple prime short run cost curve is going to be a lot flatter than the k double prime short run cost curve, which in itself is a lot flatter than the short run cost curve corresponding to k prime amount of capital. And we said that in the long run, I can seamlessly change capital from k prime to k double prime to k triple prime. So, how will the firm decide which level of capital to use? Well, that is going to be based on, well, what is the amount of output it wants to produce. If it wants to produce output between 0 and q prime, it will choose k prime amount of capital. If it wants to choose an output between q prime and q double prime, it will choose k double prime amount of capital. And finally, for q which are greater than q double prime, it will choose k triple prime amount of capital. Now, I mentioned towards the end of the lecture that the long run cost is the lower envelope of the corresponding short run cost curves. What I mean by that is that instead of just three different short run scenarios, if the firm could change k by very small amounts, right. So, think of a picture where you are giving me different values of k. So, let us say we start with a short run cost curve, right, and my k double prime equals k prime plus epsilon, where the epsilon is actually tending to 0, right. So, you are changing k by a very tiny amount, right. So, think of the smallest possible change in k that you have. So, instead of having a pronounced, so in the previous example, I took an r k prime somewhere here and then I had drawn the new blue curve, but now I will start with a fixed cost which is almost close to r k prime. In fact, I will just put a blue curve here, but notice it is going to almost coincide with the black curve. So, I am going to get a blue curve which is going to be a lot flatter than the black curve, right. Then I am going to have a k triple prime, let us say, which is k double prime plus epsilon, where the epsilon is tending to 0, right. So, now I am going to get another short run cost curve which also is going to be flatter than the blue curve. So, notice if you can change capital in infinitesimally small amounts, right. So, I am changing them by as small amounts that you can think of, then the intersections between subsequent short run cost curves is almost going to be very close and we will not even be able to see them, right. In such a case, well, what is going to be the long run cost curve? Well, the long run cost curve simply is going to pick the lowest portions of the corresponding short run cost curves, the one in red, right. So, this is going to be the long run cost, which is why I said that when k can be varied by infinitesimally small amounts, right, if the firm can change k by as small amounts as you can think of, infinitesimally small amounts, the long run cost will still continue to pick the lowest portions of the corresponding short run cost. The long run cost will be the lower envelope of the short run cost curves. Let me take an example and we will work out this example so that we understand this better, right. So, let us take the following example. Okay. We have seen versions of this example earlier, wherein we have derived the long run cost and the short run cost, but let us also make sure that we understand this completely, right. So, suppose we are given the production function Q is equals to 10 times square root of Lk, right. We are told that the per unit cost of labor is rupees 1000 per labor hour. The per unit cost of capital R is, let us say, 250, right. What are we interested in doing? We are interested in drawing the long run cost and the short run cost curve. So, we want to draw the cost in the long run and the cost in the short run. We will get to the short run cost in just a moment, right. So, suppose we start with the long run. Well, in the long run, what do we know? We are interested in finding the long run cost, which is the lowest cost incurred by the firm to produce a certain quantity Q of output, given that the input prices are as follows. So, what do I need? I need my cost minimizing bundle L star and K star to satisfy the equation of the isoquant. I also need to ensure that the tangency condition is satisfied. Now, recall the tangency condition is MPL by MPK equals W upon R. So, let us identify what MPL is. The marginal product of labor is dQ dL. So, keeping K fixed, so that is going to be 10 times root K upon 1 upon 2 root L. The derivative of root L with respect to L is 1 upon 2 root L. So, that is going to give me 5 times root K upon root L. Similarly, my MPK is going to be dQ dK, which is 10 times square root of L. Those are all, that is good. So, L is going to be constant when I am finding the derivative with respect to K, and the derivative of root K with respect to K is 1 upon 2 root K, which is 5 times root L by root K, which then implies that my MPL by MPK equals 5 root K upon root L divided by 5 root L upon root K. If you do the algebra, this will turn out to be K upon L, right. So, you will find that this is K upon L, and this must be equal to W upon R as per the tangency condition, which is 1000 divided by 250, which is going to be equal to 4. So, that is going to give me a condition K is equals to 4L, right. Now, this is no different from what we have done earlier when we solved for the cost minimizing input bundle. I have just repeated it, and since we have seen it earlier, I am just directly writing the tangency condition MPL by MPK equals W upon R. If you are not clear about this part, I would suggest that you just go back to the previous lectures, make sure you understand the cost minimization exercise, and then come back and review this. Now, I also know that the optimal L and K must satisfy the production function equation. So, Q is equals to 10 times square root of Lk and K is equals to 4L. So, 10 times square root of 4L square, which is equal to, so this will give me a 2 times L. So, this is going to be a 20 times L, which means in the long run the L as a function of Q is going to be Q upon 20. You tell me that you want to produce a certain quantity 100 units of output, the optimal L is going to be 100 divided by 20, which is equal to 5. Now, my K as a function of Q, K is going to be 4 times L. So, 4 times Q upon 20. So, that is going to be 4 times Q upon 20. So, that is Q upon 5, right. So, to produce 100 units of output, I will need 20 units of capital or 20 machines. So, what is my long run cost function? My long run cost function is the cost of labor plus the cost of capital. Notice both labor and capital are decision variables. So, 1000 times Q upon 20 is my cost of labor plus 250 times cost of capital, which is Q upon 5. So, that is going to give me 50 times Q plus a 50 times Q, which is going to give me 100 Q. So, this is my long run cost function, and notice this long run cost function is linear in output. So, if I wanted to draw the long run cost function, it is going to be a straight line with a slope which is equal to 100. We will draw the long run cost curve in a few minutes, right. So, this is about the long run. Now, what about the short run analysis, right. So, suppose in the short run that you are fixing k bar equal to 40, right. So, you are told that you have 40 machines only and I will have to produce only using these 40 machines and accordingly hire L. So, notice in the short run then the optimal amount of labor is going to come directly from the production function. So, I know Q is equals to 10 times square root of L times K, but K is now going to be 40, right. So, this means that Q square equals 100 times L times 40. So, that is going to be 4000 L, which means that the optimal amount of L in the short run given that K bar equals to 40 is going to be equal to Q square upon 4000. So, this is my optimal L. So, notice how the optimal L has changed in the short run. In the long run, the optimal L was obtained by using the condition of the isoquant as well as the tangency condition, but in the short run my optimal L has to come directly from the production function. So, the cost in the short run when you have 40 machines is the sum of the fixed cost and the variable cost. Well, what is my fixed cost? That is going to be the per unit rental rate of capital, which is 250, times the number of machines that I have, K bar equals 40, plus the cost of labor. So, the per unit wage rate is 1000 times the cost of labor, L is Q square upon 4000. So, this is W times L. So, this gives me the short run cost given that I have 40 units of capital is, so if I multiply 250 times 40, I am going to get 10,000, and the second term is going to give me a Q square upon 4. So, this is the cost in the short run. Notice the cost in the short run and the cost in the long run are not the same, right. In fact, here based on the functional forms you can say that the long run cost is linear, but the short run cost is non-linear. In fact, it is convex. So, let us try and draw them. So, if I draw the long run and the short run cost, so the long run cost is 100 times Q. So, when Q is 0, I do not need any input, I do not need labor, I do not need capital. So, my cost is going to be 0. So, this is going to be the long run cost. So, this is going to be the long run cost. So, this has a slope of 100. Now, what about my short run? Okay. So, the K bar equal to 40 is actually quite interesting, right. Now, suppose I said Q is equal to 200 units, right. So, suppose we want to produce 200 units. The cost in the long run, notice, of producing 200 units is 100 times 200. So, that is going to be rupees 20,000. The cost in the short run for producing 200 units when the amount of capital is 40 is going to be 10,000 plus 200 square divided by 4. So, this is going to be 50 times 200. So, again a 10,000. So, that is going to be rupees 20,000, right. So, essentially for producing 200 units of output, when you have 40 units of capital, the cost in the long run and the cost in the short run are equal, right. Let me repeat that part because there is something important in the statement that I just made. We said to produce 200 units of output, when the amount of capital is fixed at 40 in the short run, the short run cost will be exactly equal to the long run cost, right. We also have learnt that the long run cost can never be greater than the short run cost. Whatever I can do in the short run, I will be able to replicate in the long run, because the long run gives you more flexibility. I can not only choose labor, I can also choose capital. So, if I were to draw the short run cost here, when Q is 0, the short run cost is going to be 10,000, that is going to be the cost of capital, and then my cost in the long run, the short run is going to follow this particular curve. So, this is Q 40, right, and the point where the costs are equal corresponds to Q equals to 200 units of output, and this is 20,000. Now, you might wonder, how did I get Q equals to 200? Essentially, I want to find out what is the Q at which both the long run cost and the short run cost are equal. So, essentially, if you set CL equals to CQ, so we can solve for Q where CL is equal to CS by setting 100Q equals 10,000 plus Q square by 4. In fact, if you do that and you do the algebra, you will find that one of the roots, so this is a quadratic equation, it will have two roots, you can remove one of the roots, the relevant root is going to be Q equals to 200. What's more interesting though is, what is it that is driving, this is the arithmetic part of it, right. So, we set the two things, we computed the cost, and it turns out that the costs are equal. But notice, there is something hidden here, and we can now see that more clearly. What is so particular about Q equal to 200 is that when to produce Q equals to 200 units, let us ask, in the long run, what is the amount of labor and the amount of capital that you will use? Well, the amount of labor that you will use is going to be denoted by Q upon 20, whereas the amount of capital is going to be denoted by Q upon 5. In particular, so I will have 200 upon 20 rather. So, the amount of labor that I will use is Q divided by 5, which is, we will need 40 units of labor, sorry, Q divided by 20, right. So, Q divided by 20. So, we will need 10 units of labor, but the amount of capital that I will need is Q upon 5, which is 40. So, the optimal K and L combination are 10, 40. So, this is my optimal input bundle. But notice, the amount of capital that I am using, which is 40, is what we are fixing in the short run, right. So, if the amount of capital is fixed at K equal to 40 and you want me to produce exactly 200 units of output, notice how much labor will I need? I will need Q square upon 4000, because I obtained my labor from the production function. So, in the short run, the amount of labor that I need is Q square upon 4000, and you want me to produce 200 units. So, the amount of labor that I will need is going to be equal to 10, which is exactly what I used in the long run, right. So, what is the takeaway? The takeaway is that in the long run, you are going to be choosing both labor and capital. You found out your L star and the K star. If the K star, which is equal to 40, which is the optimal choice of capital in the long run, is exactly equal to the K that you have chosen in the short run, your long run cost and the short run cost must be the same, right. So, this is a very important finding, and let me put that on the board. If the short run amount of capital is exactly equal to the long run optimal choice, right. In the long run, you are not fixing capital, you are in fact chosen the K star, you are choosing the K star by solving the tangency condition as well as the production function condition, right. So, if the short run amount of K bar is exactly equal to the long run optimal choice of K, then the short run cost will be equal to the long run cost, right. In general, the long run cost will always be lower than the short run cost, but can it be equal? Yes, they can be equal in that specific case where the amount of K that I have chosen, which is my optimal choice of K in the long run, is the amount of K bar that I am fixing in the short run, right. So, this is a very, very important finding, and that will also help us drawing the long run and the short run cost, right. So, you can check that if the short run cost, in fact, you can check, I will put it here. if k bar was 50, right, if k bar was 50, the short run cost of producing 200 units, let us say, with 50 units of capital, and the long run cost of producing 200 units will not be the same, right, because in the long run the cost is 20,000 rupees we have identified, but you can identify what the cost in the short run is going to be when you have 50 units of capital. You will find that the cost is going to be greater than the cost that you are going to incur in the long run. So, please repeat this exercise to confirm for yourself that when I am changing the level of k bar to 50, which is not the cost minimizing choice of k in the long run, the short run cost is going to be greater than the long run cost. Okay. So, let us move on now. So, this was about the total cost curves in the long run and the short run. But what about average cost? So, how do we move from the short run average cost curves to long run average costs? So, short run average cost to long run average cost. Right. So, for that, notice average costs are always obtained from the cost curves. So, recall the three different levels of capital: k prime less than k double prime less than k triple prime. So, as before, I will have the three different cost curves. So, this is the cost when I have k prime amount of capital. I will be consistent with the colors as well, so that you also have them, k double prime, and then I have the cost in the third case of k triple prime amount of capital, right. And what did we learn? We learned that this was k prime, q prime, and this was q double prime. Okay. So, I am going to use the graph on the top to identify and draw the average cost curves, right. So, this is about k prime less than k double prime less than k triple prime. So, fixed cost in the k prime case is less than the fixed cost in the k double prime case is less than fixed cost in the k triple prime case, which is the same as before. So, I want to draw the average cost curves. And notice average cost is measured in rupees per unit of output. So, to get the average cost, what will I do? I will essentially, the average cost when the level of capital is k prime essentially is going to be the total cost divided by the q. So, I will be drawing, I will be connecting the origin to various points on the first cost curve, and notice that those angles are becoming flatter and flatter, right, and I am going to get an average cost curve which is going to be somewhat like this. So, the average cost curve, so I am going to get an average cost curve in the short run where I have k prime amount of capital, right. Now, notice so if my level of capital is k double prime, the corresponding short run cost curve is the one given in blue. So, the corresponding average cost curve is going to be the cost associated with the blue cost curve divided by the q. Now, for the same q, notice if I were to find out the corresponding point on the, so for the same q, well, when it was the black curve it was this, but now if I were to connect the origin to that point, I am going to get a steeper curve, right. So, which essentially says that if I wanted to look at the average cost curve, so I will just pull these guys down. If I wanted to find the average cost curve for the blue cost curve, right, I will find that it is going to start at a much higher level, right, and the average cost at q equals to q prime is going to be the same for both the blue and the black cases, right. So, I am going to have in blue the average cost curve is going to look somewhat like this. So, I am going to have an average cost curve for k double prime amount of capital, right. So, this is the second average cost curve. Since the costs are equal at q equal to q prime, the average costs also are equal at q equal to q prime. Now, I will repeat this exercise when the level of capital is k triple prime, right, when the level of capital is k triple prime, and notice now if it is going to start at a much higher level, right, but it is going to be equal to the average cost curve when q is equal to the blue cost curve, right. So, the average cost must be the same at q equals to q double prime. So, I am going to start with the, and it is going to intersect this here. So, I will try and be consistent with that. So, I am going to draw it. So, this is the average cost curve for k triple prime amount of capital, right. So, I am not drawing it to scale. So, all I have done is that I have taken the levels of capital. Let me just draw this part a little carefully, so that, so I am just going to have this portion here, okay. So, now this tells me that I have the 3 different short run average cost curves, and in the long run, notice what did we do? In the long run, we said that for 0 less than q less than q prime, the level of capital that I was using was k prime. So, the corresponding average cost curve that will matter is this portion of the average cost curve, right, because my level of capital was fixed at k prime. For q between q prime and q double prime, the level of capital that I was using was k double prime, right. So, the average cost curve essentially was tracing out the lowest portion of the corresponding average cost curve in the short run, and for q greater than q double prime, the level of capital that I was using is k triple prime, because that is when the lowest cost was obtained, because recall the long run cost curve was this curve given in this wiggly red curve. So, essentially I will trace out the lowest portion of the corresponding average cost. So, the one in red is my long run average cost, right. So, just as the short run cost curve was tracing the lowest portion of the corresponding, just as the long run cost curve was tracing the lowest portion of the corresponding short run cost curves, the long run average cost curve will also trace out the lowest portions of the corresponding short run average cost curve. So, let me just put that on the board, right. So, for any q, for any amount of output, the long run average cost gives the lowest cost of producing the corresponding output. Which means that the long run average cost must also give the lowest possible average cost, rather, to be more precise, the lowest average cost of producing the corresponding output. So, in other words, the long run average cost curve will trace out the lowest portions of the corresponding short run average cost curves, and if we generalize this for any small levels of capital, right, we can say that the long run average cost is the lower envelope of the corresponding short run average cost curve, right. So, just as my long run cost curve is the corresponding lower envelope, is the lower envelope of the corresponding short run cost curve, the same thing holds for the long run average cost as well. Now, in the above example, the long run cost was turned out to be 100 times q. So, the long run average cost here is the long run cost divided by q, which is equal to 100. In fact, the long run average cost was constant in that particular example, right. Now, we can combine, so that leaves us with only the marginal cost, right. So, we have done the analysis of moving from short run cost to long run cost, short run average cost to the long run average cost, which leads us to the following question: is the long run marginal cost the lower envelope of the corresponding short run marginal cost curves, right? I will let you think this for a few minutes and we will discuss drawing the long run marginal cost from the corresponding short run marginal costs. And we will close this discussion by talking a little bit about which are the important concepts in the short run versus the long run, right? In the long run, the average cost will turn out to be a very useful concept. In the short run, the marginal cost is going to be the most important concept. So, next class, I will talk about the long run marginal cost and try and answer this question. So, it is a good idea to go back and review whatever we have covered so far as drawing the cost curves are concerned. Thank you.